Good day, everyone. My name is Chris Hickman from Sumida, and I'd like to spend some time today to review the features and functions of Sumida's new metal composite cross-reference tool. The purpose of this tool is to focus on Sumida's consumer and industrial metal composite inductor product lineup. This product family of cutting-edge metal composite inductors ranges in size from 2 millimeters up to 17 millimeters, and ranges from 80 nanohenries up to 68 microhenries depending on package size. If you don't see what you need in the breadth of this product line, it is possible to request custom inductance and component specifications on a case-by-case basis. So if you have interest or questions related to this, please contact your local Sumida representatives to check into it further. Let's go ahead and get started. First, let's find the file and open it. The file name is Sumida's Metal Composite Cross-Reference Tool. This tool is Excel-based and should work on all recent versions of Microsoft Office capable of supporting macros. Let's open the file by double-clicking it. Once the file loads, please go ahead and clear out any startup flags and stabilize the file. Moving into the file, you can see it is separated into three distinct Excel tabs. The first tab being the Specification Cross-Reference tab, second, the Mechanical Cross-Reference tab, and third, the Selection Guide tab. Now the first tab we will review is the Specification Cross-Reference. This tab is set up in a filtered table containing all the parametric data from the Sumida website and the component specifications. Before I get started on the table itself, I wanted to show you the Quick Zoom Adjustment button at the upper left hand of the screen. By clicking the red button, you can automatically adjust the screen zoom in Excel to show all the columns of the data table for easier use. There's a similar button on all three tabs. If you like a greater zoom, you can go ahead and manually adjust the screen to your preference. Now that we are all set up, let's review the table. The key parameters covered in the table are, first, the Sumida type name. This is the type or series name. The first digits are the mechanical package size. The later alpha characters represent the architecture and material of the construction. Next is the manufacturing part number. The prefix is the type name followed by the market standard inductance, tolerance, and packaging codes. Next, inductance in microhenries. The nominal tolerance on these parts is M, or 20%. Next is DCR, or DC resistance, measured in milliohms. Both max and typical values are available. Followed by saturation current in amps at both 20% or 30% inductance drop. Again, both max and typical values are available, but the max meaning here is a little different than it is for DC resistance. Here, the typical numbers are the current levels that Sumida will guarantee the vast majority of parts can handle. The max number is actually the minimum level of current Sumida will guarantee that all parts can hit. The max number is always lower than the typical. Next column is temperature rise current. This is the typical amount of current needed to raise the temperature of the inductor by 40 degrees C. The next columns are mechanical package size. This is the length, width, and height of the part in millimeters max. Also included in the table, but not in a sortable format, is the pad geometry. This is the recommended PC board layout in millimeters typical. Followed by withstand voltage specifications. This is the maximum voltage across the inductor. This is the maximum voltage, voltage in minus voltage out, that the inductor should see in the circuit. Above this, and it is possible to degrade and, in the worst case, damage the part. And finally, normal operating temperature range. This is the full temperature range specified for these inductors. This temperature range includes the self-temp rise of the inductor. So since these parts have a 40 degree C temperature rise specification, the actual maximum ambient temperature of the surrounding environment would be about 85 C worst case at max current. As mentioned previously, any column with a drop-down arrow can be filtered for the data. Now let's work on some examples. For instance, if you wanted to see the specification for all parts with a 10 microhenry inductance, you would simply go to the inductance column, click the drop-down, unselect all, and then scroll to find 10 microhenries and click on it, click OK, and now the table will be sorted for all 10 microhenry parts in all available families. Now with the table sorted, you can review the list for 10 microhenry parts of interest and look at the specifications loaded in the table. But if you want to see what is the total amount of information Sumida has available on this part, all you need to do is single click on the Sumida type name in the type column, and it will jump to the Sumida website for this part family so you can review everything that's available. Let's try it now. To review the custom sort, just return to the drop-down and remove the sort from the list. Now the table is returned to its original status. Now for a little tighter focus sort, you can use the number sort feature in Excel. In this example, we would like to see all the available parts that have a 20% saturation current of greater than 10 amps. Now we go to the 20% saturation column, go to the drop-down, select number filters, go to greater than or equal to. Now in the field we load in 10, click OK, and now the table is sorted for all parts for all families that have a 20% saturation current above 10 amps. Again, to clear this out, just re-click the drop down and clear the filter to return the table to its original status. Now it is also possible to set up progressive or multi-layer sorting in the table based on multiple columns, say for a combination of inductance and saturation current, but in most circumstances one filter would normally get the list small enough for a visual review. Two other features I want to touch on before we move on. Number one, as described earlier, each entry in the Sumida type column is hyperlinked with the Sumida website for that part type. Just select a cell in that column and click it once, and it should jump to the website if the computer is connected to the internet. Secondly, the purple buttons located up in the mechanical package columns. These buttons represent each family size of inductors from the smallest 2016 to the largest 17mm part. If you click the button, it will scroll the table automatically and bring that family to the top of the table. There's also a button labeled Mechanical Cross-Reference that will jump the file to the Mechanical Cross-Reference tab immediately. There's a sister button on this tab that will jump back. Now for some final housekeeping. There are unfortunately some families of inductors where the current is measured at both 20 and 30%, but there are a few that are only measured at one of them. Keep this in mind when setting up your sorts, as you may have to look at both 20% and 30% numbers to get the full list. Now moving on to the mechanical cross-reference. This tab is a bit simpler and the review should be pretty quick. Now as before, it has the auto zoom adjustment button in the upper left hand should you need it. Click it to adjust the screen to show the desired columns for the review. In general, the purpose of this tab is to graphically see what sizes of metal composite inductors are currently available from Sumida. Each family has a button created that hyperlinks back to the family list in the specification cross-reference tab. We have used both metric and English part size nomenclatures to show the X and Y axis of the part size, and on the Z axis we use millimeter for the height. To use the sheet, just find the size part that interests you and click the blue button. The sheet will then jump to a pre-scrolled specification table. To jump back, click the purple Mechanical Cross-Reference tab button located in the mechanical package size area. Now let us complete our review and go to the Selection Guide tab. The function of this tab is to take the user circuit condition inputs, calculate the estimated current numbers, and then propose some suggested inductor solutions from Sumida's industrial and consumer metal composite inductor families. Now some general housekeeping and review on this slide. There's the same auto zoom button at the top left of the screen to adjust the screen if the user needs it. There's also some general instructions at the bottom left of the screen. This is intended to help outside this training video. Let's start the review in the manual input section, colored in light green in the upper left. This is the section where the user inputs their circuit conditions. The key parameters here are input voltage, Vn, loaded in volts. This cell will allow any input between 0.001 volts and 1000 volts. Next, output current, Vout, loaded in volts also. This cell also will allow for an input between 0.001 volts and 1000 volts. Following, output current, IRMS, loaded in amps. This cell will allow any input above 0.001 amps. Followed by target ripple. This cell allows for 3 different types of inputs. The user can choose auto mode, percent mode, or amp mode by selecting the desired mode in the unit column drop-down box. If the user selects auto, the input value is hidden and the sheet will use the standard calculations to derive the ripple current based on the VIN, Vout, and output current. If the user selects percent mode, the sheet will use the percent value loaded in the cell to calculate all the required current numbers. As a default, the duty cycle is set to 50%. This is common in the industry for all these type of sheets. If the user selects A or amp mode, the sheet will use the amp value loaded in the target ripple cell to calculate all the required current numbers. Again, the duty cycle will be automatically set at 50%. Followed by switching frequency, loaded in kilohertz. This cell will allow an input between 0.001 kilohertz and 10,000 kilohertz. The next row is the switcher topology. This is not directly user selected, but is assigned based on the VIN, Vout inputs the user is loaded. In this cell, the sheet will tell you which switcher topology and associated calculations it will be using. In this case, it's in buck mode. But if you input a VIN below the Vout data, the sheet would automatically change into boost mode. This sheet will only do buck or boost in continuous current mode. Unfortunately, this sheet will not work 100% correctly for discontinuous mode switchers or buck boost switchers. Please note that as the user inputs their conditions into the green area, the sheet will be auto-calculating on every input, but the true results will not be done until the user inputs all their circuit-specific parameters. As the user's parameters are loaded into the light green section, the sheet will be doing numerous things in the background. It will be calculating max current, min current, ripple current. It will generate a graphical representation of the inductor cycle waveform on time, the chart to the right. This chart shows the calculated ripple, that's the blue sawtooth waveform, superimposed on the user inputted output current, the black dotted line. If you would like to magnify this chart, just hit the red magnifier button to zoom in on the chart, and then again to return to the original status of the sheet. While we are focusing on this section, let's try to get familiar with the calculated results and their graphical representations in the chart. First is Imax. This represents the maximum current swing based on the circuit inputs. You can see this in the graphical representation on the chart to the right. The max current level is shown as the orange dotted line and the top peak of the waveform. Next is Imin, the estimated minimum current swing based on the circuit inputs. You can see this in the graphical representation as the minimum level of the gray dotted line and the minimum peak. Following is iRipple, the total ripple. This is the difference between the Imax and the Imin current. The sheet will show you both this value in amps and the percent mode. In the graphical representation, the ripple current is the swinging blue line, and the total ripple number is the difference between the top peak and the bottom peak. Next is iInput. This is the calculated input current through the inductor needed to generate the specified output power. Next is duty. This is the ratio that represents the amount of time that the switching circuit is turned on versus the amount of time it is turned off to maintain the required output power. A duty ratio of 0.5 represents a circuit that is powered on 50% of the time. Therefore, a duty ratio of 0.4 would represent a circuit that is only turned on 40% of the time. Next in the list, on time. This is the amount of time in microseconds that the circuit is left turned on during its switching cycles. You were able to see this in the graphical representation by the amount of time it takes on the x-axis to climb from the bottom valley of the waveform to the top peak. In this example, that's 1 microsecond. Next is the cycle time. This is the amount of time in microseconds it takes the circuit to complete 1 full cycle of on time and off time. You were able to see this in the graphical representation by the amount of time it takes on the x-axis to climb from the bottom valley of the waveform to the top peak and then return to the valley. In this example, that would be 2 microseconds. It will then perform a calculation to establish a target inductance value. This inductance calculation is based upon a well-established industry standard methodology. The sheet will then use that reference inductance calculation to look through all available parts and recommend a possible inductor solution in every available size metal component inductor that fits the inductance and current requirements set above. These it will show on the table in the lower right that's named Suggested Part Number Summary. One possible solution in each available size will be shown. If no solution is available in that size, it will just show as no part based on the inputs. If you would like to magnify this chart, just hit the red magnifier button to zoom in on the chart, and then again to go back to its original format. It is also possible to hyperlink to the parametric specifications in the Specification Cross-Reference tab by clicking one time on the desired type name in the table. The file will then jump to the specification table in the Specification Cross-Reference tab, pre-sorted for the family type you've selected. To move back, just reselect the Selection Guide tab. Based on the automatic part number review conducted by the sheet, the smallest available solution from this list will be preloaded into the part number selection area. This is the gray area to the left. From this component selection, the sheet will load up all the standard parametric data for the part, such as DCR, ISAT, iTemp, withstand voltage, and operating temp. The final three rows in this area are for the inductance value reference calculation we previously discussed, followed by two suggested inductor solutions, the first being the smallest part available that meets the conditions generated by the user's input conditions. To ease use of the sheet, this is the part number that is already preloaded in the drop-down box in the gray area. But there's also a secondary suggestion which is a bit more conservative. This is the next largest size that meets the requirements. It is also possible to disregard the auto suggestions and manually select any available metal composite part number from the drop-down box in gray. Just click on the arrow and select any part you want. It will again update the parametric specifications, including the mechanical package information in the brown area over here. Both part geometry and recommended land pattern for the PCB will be loaded. It will also let you know if the part you selected has a viable solution based on the inputs and associated calculations. If all is okay, the alerts and warning area should stay green, but if there's an issue, an area will highlight red and list out the type of error. Normally this is related to insufficient current capability, such as the below example. Another way to select parts is to go back over the suggested part number table and select the part number from the table using the radial buttons next to the size. Clicking the radial button will load that part number into the gray area and recalculate the sheet based on the input. If you select a part number that has no solution listed, the sheet will automatically just jump to the smallest part available. Now that we're a bit more familiar with the sheet, let's run a simple example of a buck converter. In this example, we're going to use an input voltage of 13.6 volts, an output voltage of 3.3 volts, an output current of 1.5 amps, a target ripple of 30%, so we will put 30 and change to percent mode, and then a switching frequency of 1 megahertz or 1000 kilohertz. Sheet is calculated. Now, based on the calculations in the sheet, the smallest part available would be an 0415 CDMCC DS-4R7MC. That's a 4.7 microhenry part with 130 milliohm DCR and an ISAT current of 3 amps. Now, if we want to see all the available solutions, we can go to the suggested part number summary table and look at all the available selections. So there are parts available from 4 millimeters all the way up to 17 millimeters. The user can then select the part most suitable for their design. Let's try another example. This time we will simulate a boost application with an input voltage of 5 volts, output voltage of 12, an output current of 0.5 amps, with a target ripple of 25% and a switching frequency of 500 kilohertz. So we go to the sheet, load 5 volts as the input, 12 volts as the output, change the output current to 0.5 amps, change the target ripple percent to 25%, and now change the switching frequency to 500 kilohertz. Now the sheet has completed its calculation, and the smallest part available for this design would be an 0624 CDMC CDS-220MC. This is a 22 microhenry inductor with a DCR of 242 milliohms and an ISAT of 3.2 amps. And again, you could go to the table and look at all the available solutions for this application. That about covers all the key features and functions of this tool. I hope you have found this review some benefit. If you have further questions or comments, please contact your local Sumida representative and we can help you out further. Thank you for your time and have a great rest of your day.